That clock gets faster and faster. It's now 5 minutes fast. That's significant.
Maybe it's a quantum clock and I've found something that works.
It's like the clocks at work. They'll get out of sync because it's like I work at a pool. So you have one clock at one end of the lane and one clock at the other end of the
Yeah.
lane. And they'll get out of sync or they'll get like 20 minutes ahead. So I'm trying to run lessons and I can't figure out what time it is to end my lesson.
See, 5 minutes makes a difference. Welcome to my world.
It's different, especially when you're working with little kids.
Because the difference is I have like a time right here that I can trust, or my phone, but not when you're in the water, I would assume.
I'll watch the pool.
Yeah.
It doesn't work well. They don't like it.
Okay. Everybody got the notes? Blackboard, new notes. Okay. All right. So I actually think that this chapter, certainly the math stuff, is a little bit easier than what we were just doing, which is good because you guys did well on the exam. So, just hope for even better. 18 is probably similar to what 16 was. It's a little bit more challenging, but 17 is pretty straightforward. Okay, so we have to do some of the concept stuff first about what acids and bases are. Hopefully, because you did the pre-class activity, you've got like a general sense of these more formal definitions. So it's interesting because acids and bases, we use those terms in everyday life, but not a lot of people understand what they mean, chemistry-wise. So you probably read about some of the properties, like acids are sour, they're corrosive. Bases are actually also corrosive, so why that matters, not sure. Bases are slippery, so like soap is a good example of a base, or like if you've ever touched bleach or even diluted bleach, it feels slippery. And they taste bitter. Did I say that already? So spinach, dark chocolate, those are bases. Tomatoes, lemon juice, those are acids. Okay, but then we always tell you don't taste anything in lab, so keep that in mind. All right, there's 2 definitions of acids and bases. They were kind of developed by different people, and they're slightly different, but both of them are useful for understanding and identifying an acid or base. So the first one is what products they make. So an acid produces either H plus, or another word we use for H plus is H3O plus. So if you look at water and you add an H plus to it, you get H3O plus. So I was thinking of why do I prefer H3O plus? And then as I got through last class, I realized why. There's one example when you do it with bases where it just makes sense to include the water. So when you see H plus or H3O plus, they literally mean the same thing. It's just personal preference of whether you include the water in a reaction or not. Okay? Remember, hydrogen is just a proton. There's no neutrons in hydrogen. So it's a proton and a single electron. So H plus is the electron has left. Look at where it is in the periodic table. It's in that first column. And so it's not a metal. It's not lithium or sodium. It's not like those in that sense. But it does behave that way when we're looking at acids and bases. So it will actually donate that electron, like it'll give it up, it'll lose it, just like lithium and sodium do, and it'll become H plus. So if it loses that electron, why does that keep happening? It's like, I hate stuff like this tiny little, I used to use a wireless one, which I love. I miss it so much. But it died and I wasn't willing to replace it because it only lasted for like 6 months. Okay. But that would avoid this thing. Okay. So when you lose that electron, it's just a proton now. So you will often hear people refer to H plus as a proton. So when we talk about an acid losing an H plus, you'll hear people say that it loses a proton. When we look at bases, the product that they make is OH minus from polyatomic ions. Remember, this is called hydroxide. So for a base, when it reacts in water, you will see hydroxide produced. Now, Arrhenius is kind of limiting because it's looking at an acid specifically only with water. It's not looking at what if I combine an acid and a base. So sodium hydroxide and hydrochloric acid. It's looking at if I have this thing in water. So in water for the Arrhenius definition. The Bronsted-Lowry one is a little bit broader, I think. It talks about it as either donating or accepting an H+. So to make this one make sense, let's look at the example on the next page. Okay, so HCl goes into water. It breaks apart, actually really similar to how like sodium chloride would, and it forms H+ and Cl-. I like to write this showing the water, so I would write it as HCl plus water, which would then mean that the H+ is H3O+, because this is kind of showing you, like I talked about, why they're the same thing. It's basically like showing that H+ hooking up with a single water molecule and adding on to it, like actually bonding with it. This is probably similar to what happens in reality. It probably looks a little bit more like what sodium does, where you have waters surrounding the ion. But we have to pick a way to represent it. So some people like to do H+, some people like to do H3O+. Okay? So when I do it, I do H3O+, and then, I guess I didn't think about where I was drawing that. Then also the ion. And the reason I like this better is because it fits with the Bronsted-Lowry definition a little bit better. So the Bronsted-Lowry definition of an acid says it's going to donate the H+. So this hydrogen on the HCl is given to a water molecule. So it's donating it to the water molecule. So when you show the water, it's a little bit easier to see that than if it just kind of breaks apart. So it's donating it to the water becomes H3O+, and the chlorine is left behind. Now, an important part of this is the charges. Because you're just moving the hydrogen, you're not moving the hydrogen's electron, the thing that the acid turns into will always have, I don't want to write that arrow. Let me just highlight them. So this is the acid. This is the thing the acid turns into. Pretty quickly here, we're going to give that a name. It's called the conjugate base. I don't want to lose track of my thoughts, so let's not talk about why it's called that yet. So the thing the acid turns into is going to have one less hydrogen because it's donating that hydrogen, but the hydrogen leaves its electron behind, so it's also going to have a reduced charge. So it's a negative charge because that hydrogen left its electron behind.
Is the H3O plus then the conjugate acid?
It is. So in this instance, the water is actually acting as the base. The Bronsted-Lowry definition tells us that a base accepts a proton. So water can act as either an acid or a base, and it basically does whatever the other thing doesn't want to do. So if there's an acid in there, water will act as a base. If there's a base in there, water is going to act as the acid. So because it's acting as a base, It's accepting the proton, or the H+, and then it's turning into H3O+, and that is called the conjugate acid. Again, one more hydrogen now, and one more charge unit. So like it increased in charge. So it's really important you keep track of the charges, not just the hydrogens. So whenever people get going with this, I'm always like, it's losing a hydrogen, so make sure it also loses a charge unit. It goes down in charge. So it goes from 0 as HCl to -1. So it lost a hydrogen, lost a charge unit. For the H2O, it gained a hydrogen and it gained a charge unit. Okay, good. Let's actually start with the second type of bases because I think they're actually a little easier to understand. So we're still in water, but now we're talking about NH3 acting as a base. And like I said before, water will do whatever the other thing doesn't want to do. So in this instance, water is going to act as the acid. This is because when you think about it as a proton donor, there always has to be something giving up the proton and the H+, and something taking the H+. And so you're always going to have an acid and a base. You can't have one without the other. It has to be something to take the H+ if it's going to give it up. Okay? So the base definition is that it accepts a proton, and the acid definition is that it donates it. So that means that this hydrogen is coming from the water and going to the NH3. So that NH3 turns into NH4 with a positive charge because the water didn't bring its electron with it. And the water turned into OH minus because it left its electrons behind. And we can go ahead and label those as well. The NH3 would be the conjugate acid, and maybe we'll talk about why here. And OH minus would be the conjugate base. And also you can see the other definition of a base is that it produces OH minus, and one of the products here is OH minus. So you stick ammonia, NH3, in water, it will produce OH minus, so that's the Arrhenius definition, and the Bronsted-Lowry definition, it produces the OH minus by accepting that H+ from the water. Okay, why is it called conjugate acid base? Because remember, if you have a, relatively even, a K of 10 or 1 or negative, or not negative, 0.1, 0.01, okay? So a K around 1, that's telling you equilibrium constant. I'm still talking about equilibrium. That's telling you that the reaction can go both directions. That's why we have a double-headed arrow, okay? So if we think of the reverse reaction, I should have my pen pointing that way. If we think of the reverse reaction, NH4, when it turns into NH3, it donated a proton to get there. So it is acting as an acid in this direction. Okay, that's why we call it the conjugate acid. Same thing with the base. OH minus is going to accept that proton and turn into water, so it is acting as a base in this direction. But it'll also always be like the thing it's paired up with, right? Like the base turns into the conjugate acid, the acid turns into the conjugate base. So if you're like, don't want to understand, you just want to memorize, there you go. Okay, the other type of base is very unique from all these other ones that we've looked at. And that is when the hydroxide ion is a salt, meaning an ionic compound, with a metal. So the most common ones we see are the 1A elements, so lithium, sodium, potassium, etc. Sodium hydroxide, like you can get solid Drano, it's like little pellets, is literally just sodium hydroxide, and then you add the water and it dissolves and eats away at the hair and gunk and probably your pipes too. I still use it sometimes. You will also see some not completely soluble, but some 2A element hydroxides. So calcium hydroxide, magnesium hydroxide. And we'll do an example reaction with these because when they dissolve, they actually break apart into 2 hydroxide ions. So this is happening in water. Water is implied there because it says aqueous. But water is not an active participant. It's not, accepting or donating a hydrogen. This is the one example where you kind of have a base without having an acid, because it is literally just breaking apart into sodium and hydroxide. And so you get hydroxide in the water, the solution, but it's not there as a result of accepting or donating a proton. It's there simply because it dissolved and broke apart. So this one actually does not fit the Bronsted-Lowry definition of a base. But when we say base, we mean how much OH minus is in there. Like when we say basic, let me rephrase that. When we say something is basic and how basic it is, the other word for that is alkalinity. If you say how alkaline something is, you mean how much OH minus is in there. So this very much changes the OH minus concentration, even though it doesn't behave according to the Bronsted-Lowry definition by accepting H+. And then just because I didn't mention it before, when we talk about something being acidic, we're talking about how much H3O plus is in there. So like if you had a 1 molar solution of HCl, you're going to have a certain amount, you're going to have 1 molar H3O plus. If you have 2 molar HCl though, you're going to have 2 molar H3O plus. So that's why we care about how much of it is in there. And this will become even more important when we start talking about a strong acid versus a weak acid. Okay, let's practice writing some equations to show. So each of these, you're going to write them as an acid reacting in water. So water is the base in these examples. And then the next one, these are all bases. So you're going to show them reacting with water. So water would be the acid in those instances. And I'll do at least 1 or 2 of them while you're working so you can check your answers as well. Oh, there's a C missing in that second one. That should be CH3COOH. Okay, we'll talk through these because there's like some minute points that I want to make sure you guys are clear on. So as you're checking your answers, make sure you don't just have the formula right, but you have the charge correct as well, because that is an important part of acid base. So the first one here should be pretty okay. You make sure you get rid of that hydrogen from the HNO3. It turns into NO3 minus, and that hydrogen goes to the water, making it HO3 plus. So like notice everything makes HO3 plus here, H3O plus. I knew that sounded wrong coming out, and I was like, what did I do there? H3O plus. This is called hydronium ion. Maybe I should like throw that out there so that I don't have to say H3O plus all the time. Hydronium. So hydroxide is OH minus. Hydronium is H3O plus. Okay, on the second one, it might be the only like confusing point might be, well, which hydrogen do I remove? Now, technically, it's not like wrong because you could write this as C2H4O2, and then when you wrote the product, you would just write one less hydrogen, okay? So it's not like it's wrong necessarily, but they are trying to not only tell you about the structure, but it also hints at which of those hydrogens is acidic. So if you see a hydrogen off by itself, not paired up with the other hydrogens, that's the one that's going to be acidic or donated. And the reason why that happens is because if you remember from like Lewis structures, this looks like this. And when you have a non-polar bond like a CH, it's really unlikely to lose that hydrogen. When you have OH, that one is, it's very polar, and so it starts to look not ionic, but it looks more like an ionic bond. And that's why the hydrogen can leave just like a sodium could leave if it was, you know, bonded with oxygen or something. So acid base is actually kind of this weird middle ground between ionic and covalent reactions. Because the hydrogen is in these covalent molecules, but it behaves like an ion. I mean, it is an ion. It behaves like metal. And the reason it's in that middle ground is because they're typically pretty polar bonds that this happens to. Okay, and then the last one here, H3PO4. So I didn't talk about naming at all. I'm not gonna like require you to know all the naming, but just so that you get comfortable if you're reading them or hearing them. It's a lot of the times these are coming from polyatomic ions. So you can see NO3 minus is nitrate. That would be nitric acid. So we just changed the ending. This is acetate ion. It's acetic acid. And then phosphate, phosphoric acid. Okay. And then it will always have, when those polyatomic ions turn into an acid, they will always have enough hydrogens to balance them out. So PO4 is PO4 3 minus, and that's why the acid form is H3PO4. NO3 was NO3 minus as the polyatomic ion, so it just needs one more hydrogen. However, with these ones that had bigger charges, bigger negative charges, and so therefore ended up with more hydrogens, they are actually very often polyprotic, meaning that they can donate multiple polyprotons protic. Okay, so this H2PO4 can actually go on and continue to donate hydrogens, and you can do it 3 times. We do write them separately. We don't usually show them as like one reaction because the first one ends up having a lot more influence than the other two. When we get to talking about equilibriums of these acid reactions, that will probably make sense because we'll look at the K. Basically, the first one has a bigger K, and it gets smaller as it goes on. So it's like less and less important. But in a small way, they do contribute to the hydronium ion concentration, which, like we said, is what defines something as being acidic. So if you have more hydronium ion because you donated more protons, then it's going to be more acidic. This is why people think of sulfuric acid as like so dangerous, because if you had HCl and H2SO4 and you had like, you know, the same concentrations, let's say they're both 2 molar, you would get more more H3O plus, more hydronium ion from the H2SO4 than you would from the HCl, even though you have the same number of moles, because H2SO4 can go on and donate that second hydrogen as well. Diprotic is what we call H2SO4. Okay, bases. So we actually have seen both the top one and the bottom one we saw exactly. The top one we basically saw it was sodium instead. I probably should include aqueous on these just so like we know that that's implied, even though the water's not written there. These very well may have started off as a solid because they are an ionic compound. Ammonia, on the other hand, is only like actually formed as a liquid. You have to like bubble. What do you bubble through there? It's not just nitrogen and hydrogen. I don't remember. Anyway, you bubble gases through water and get them to react and form ammonia. So it's already in water. Okay, so the only one that's a little different here is the calcium hydroxide. So in this one, you end up forming 2 hydroxide ions for every 1 calcium hydroxide that you have. So similar to a polyprotic acid, this one's going to have more effect on the pH. I just said that, and we haven't talked about pH yet. I know you guys like did it in the intro thing, but it's going to have more effect on the alkalinity, which is another name for how basic it is, because you're going to produce more OH minus. You're going to produce twice as much versus KOH. There are kind of other factors involved there, but that is the general idea.
Are you able to do the second one? Can you like write out the water?
If you did, you would just have water on one side and water on the other. So like if you showed this, it would just be water over here as well. So it would be like a spectator molecule.
Okay.
Yeah,
So it doesn't actually like react.
that's right.
Okay.
So any of these ones that are hydroxide ionic compounds are not involving water directly, which means that they're not actually donating a hydrogen. It's just making OH.
So it was like that unique case.
Mm-hmm.
Okay.
Yep.
Okay.
And it's fine if you show the water. I mean, also recognize most of the things we do are multiple choice. So like, I'm not gonna show you the water and not the water because they're both correct. But it's certainly not wrong if you put it down. Okay, let's do acids and bases reacting with each other when we're not having water as the acid or the base. Okay, so I'm gonna do the first two, and then I'm gonna have you do the next, not all of those. Maybe we'll do like this one and these ones, because those are a little bit interesting. Okay. All right, so the same thing applies as far as proton donor, proton acceptor, but now it's not water that's doing the donating and the accepting, okay? So if it helps you, just like show the hydrogen moving from the acid to the base. So you get F minus after that hydrogen leaves, and NH4 plus. Again, it's, putting the state of aqueous reminds you that the water, it's in water. It's just the water's not actually acting in this one. It's not acting as the acid or the base because you already have an acid and a base in there.
So is this one's considered to be like strong acid and base since there's not a double-headed arrow?
No, no. And you don't know why yet, but I should put a double arrow there. These ones up here, like this should be a double arrow. This should be a double arrow. This should be a double arrow, but this one is not. So there are basically 6 strong acids that only go to the product side. And they're in your exam equation sheet. And then the strong bases are actually just the hydroxide salts. So 1A elements, some of the 2A with hydroxide. Those are the only strong bases. And then I'm going to go ahead and label the conjugate base and conjugate acid as well. I know there's like slides on this coming up, but it's better to do it when we have the examples, and then the slides are kind of there as like reminders in case you forget. The next one's a little bit weird, mostly because the sodium is just a spectator ion. So you can include it, but it's not actually doing anything. Because once you stick sodium hydroxide in, it just becomes Na plus and OH minus. And then that Na plus doesn't do anything in this reaction. So maybe I'll write it both ways so that you can see it, but it's not really relevant. So if you were to show it, NaOH with HCl. Now, I didn't tell you in this one which one was the acid and which one was the base. You are going to know eventually. They're both strong acid. Like this NaOH is a strong base and HCl is a strong acid. So if they're on this list of strong acids and bases, well, then you're going to know that they're acids and bases. You can also infer this because it's an ionic compound with a hydroxide. But don't forget, you have seen like little OHs on the end of things. This is not hydroxide, okay? That's an alcohol. It's an OH on the end, but it's not bonded to a metal. So it's not a metal ionic hydroxide. It's not a base. It's an alcohol, which will behave as an acid. So I will probably tell you a lot of the time, but you will also get a feel for it, and it will be less confusing to know which one is going to accept and donate, okay? So the HCl is the acid. It gives it to the OH minus and becomes H2O plus, H2O. And sodium is left over and chlorine is left over. So the other way that you might see this written is OH minus plus HCl forming water plus Cl minus. And you could even write this together, like NaOH plus HCl forms water and NaCl. So if you took Drano and correctly neutralized it with hydrochloric acid, you could drink it because it's just salt water. Fascinating, right? I don't recommend it, but, you know, just because I don't know if you'll do it right. Okay, why don't you practice the ones I've starred? So the first one here and then the first two on the next page. And we'll just see where we are at that point.
Is it a standard to write the acid first and its reactions, or did I?
I feel like I always do. You definitely don't have to though, but I feel like I always do write acid and then base. Of course, if it's water, then you're definitely writing base and then water, so yeah. So since we just talked about it, I'll write the acid first here. So same thing, acids donating an H plus to the base. So you get one less hydrogen and you get one less charge unit. And then the base has one more hydrogen and one more charge unit. And this would be a weak acid, weak base. So we would have that double arrow. And we should have time. We'll just talk about that at the end so everyone's like on the same page. Okay, work these last two. Make sure you pay attention to which one's the acid and which one's the base. Okay, so these guys that can either act as an acid or a base, like water, right? Because water can do that as well, are called amphiprotic. I think amphoteric is actually water specifically, but amphiprotic, so they can have protons can be accepted or donated. Oh, I just had a flashback to when I taught this class last summer. I hate summer classes. It was 4 hours long
Ew.
once a week. Can you imagine this class?
No, Laura.
I only ever really went 3 hours, but even that, and we would take a break in the middle for like 15 minutes, but like, it was awful. I told Dr. Badger, I'm like, I'm done. I'm not doing summers. I'll grow flowers, thank you. I'm not doing summers. Like, I know it's only once a week. It seems like stupid to turn down the money of an entire class just for once a week, but it was so painful.
Mauer was telling me about that.
Who was?
Dr. Mauer.
I don't know why we do it. I would rather do 3 times a week, 2 hours, right? Like, that seems very achievable to me. Okay, so we already talked about acid-base pairs, conjugate acids. We're not going to go through that because we already talked through it. And then just before we leave, I just want to talk about what we mean by strong and weak. We kind of already discussed it, but let's be really clear. So these are the 6 strong acids. They're on your exam equation sheet. They're the halogens, but not HF. It doesn't matter why. Whatever. It's those 3 halogens though, and then nitric, perchloric, and sulfuric. And what we mean is that the K is really, really big. Okay, so the direction, the reaction is so product favored that we don't even consider the reverse reaction. So this is why we would just use the single arrow to describe this process, because we're saying the reverse reaction does not happen to any significant degree. Okay, so every single molecule of HCl will form a molecule of Cl- and a molecule of H3O+. Which means if you have a 1.8 molar solution of HCl dissolved in water, you will then have 1.8 molar hydronium ion, H3O+. So it makes like calculating pHs and stuff really, really easy. Weak acids, you can guess, have Ks that are less than 1. So if it's an acid and it's not one of the 6 strong acids that we described before, it's weak. That's not to say there aren't examples of other strong acids, but nothing you're going to encounter. So if I give you another thing and I say it's an acid, you can assume that it's a weak acid. How weak it is, we would have to know the K value. Okay, so if I had HF reacting in water, I'm going to show it with a double arrow. And if I had 1.8 molar of this, maybe I only have like 0.2 molar H3O+. Or maybe it's 1.2 molar of H3O+. We don't know without knowing the K. So where we'll start next class is doing an equilibrium problem, just like in 16, to figure out how much H3O+ there is for a particular weak acid if we know it's K. And we did not get to that point in my last class, so I won't go any further. All right, that's it. Happy Monday. Did anybody